I will be talking today about entanglement, teleportation, and Bell's inequalities. So this will be a theoretical introduction to the ideas behind last year's Nobel Prize. So the outline of the talk is pretty straightforward, in the same order as the title. And here I included some references. I will mostly be using the textbooks by Nielsen and Chuang, Quantum Information, Quantum Computations, but I also included some original sources, so the teleportation paper by Charlie Bennett and the citation to the Bell inequality that I'm going to talk about. There is more of them. Okay, so we want to start by talking about entanglement, and to talk about entanglement we need to first introduce quantum bits or qubits, and this is an idea based on making bits more quantum. So when you're talking about bits, you're talking about a situation where something can have one of two states, which are traditionally labeled as 0 and 1. Here we are going to talk about a two-level quantum system with quantum states labeled 0 and 1, and these two are basis states. So this is what we call a computational basis, and the actual difference between classical computation and quantum computations is that if we are dealing with quantum mechanics, we can not only have something in state 0 or in state 1, we also can have any superposition. So our system can be in any state psi, which is a superposition of state 0 and state 1, and obviously alpha and beta are complex numbers, and the state has to be normalized. So this is more or less it in terms of qubits. Now we can talk about entanglement, and we are going to talk about concepts illustrating them on the simplest possible system. So we are going to be talking about entanglement of two qubits. This notion of two-qubit entanglement is going to be enough to demonstrate the original version of teleportation and to show you what is behind Bell's inequalities. Okay, so entanglement, meaning quantum correlations. We have two qubits, so the most natural way of writing the two-qubit basis is in this computational single qubit basis written above. So we have four bases, state 0, 0, 0, 1, 1, 0, and 1, 1. So I use the shorthand notation. So a state ij means that qubit A is in state I and qubit B is in state j. So if we have a state of two qubits, C01, ij, I meant to say, ij, it's not a big change, and obviously these coefficients also have to be normalized. So now the question is state psi entangled or not? And the easiest way to check for entanglement is to check separability. A state is separable if and only if it's not entangled. So for pure state, a state is separable. Separability if and only if it can be written in product form. And I'm running out of these letters. So this gets quite a bit more complicated for mixed states, but we still want to be in this, well, in the situation where everything is as simple as possible. Okay, so that's about it. If you can't write a state in such a form, it means it's entangled. And here we will introduce something which is called the Bell basis. The Bell basis is a 2-qubit basis where all 4 basis states are maximally entangled. We will be using this quite a bit. So it's an equal superposition of the 0, 0 and 1, 1 states. Two of the Bell states are these equal superpositions with either a plus or a minus, and the other 2 Bell states are the equal superpositions of the other 2 states. And this is a very useful concept. Obviously, we could change the single qubit basis and get different entangled states, but yeah, we're going to stay in the traditional way that the basis that the Bell basis is written. So we need at least one of these Bell basis states so I can show you why entanglement is special. So the question we will be trying to answer here for a couple of minutes is what is the difference between quantum and classical correlations? And we are going to take one of the maximally entangled Bell states, the 0, 0, and 1, 1, and we are going to see how it behaves in comparison to a state with maximal classical correlations. So here for classical correlations we need to use the density matrix, but we are going to use a state which is analogous to this Bell state, so a state which is a mixture of the 0, 0 state and the 1, 1 state with probabilities 1/2. So the difference between these 2 states is we would write the Bell state with in the density matrix form, we would have 2 more terms correlating to the coherences to the quantum bit. Now, when people talk about entanglement, what they say that the second part is that if you measure qubit A in a given basis, then you automatically know the state of qubit B both from measurement of qubit A without even changing on qubit B. Let's say that if you measure qubit A in quantification basis, then you will perform a progressive measurement measurement on the classically correlated state. So these are operators. Let's perform the measurement of qubit A if we know that the outcome of the measurement is state 1. So we have the state 0, 0. This acts on qubit A. So this is on this times, I'm acting on this first term, times unity operator on the state of qubit B. I of course lost the normalization factor, and let's use this operator on the other bit. In the other part of the superposition we have 1, 1. Of course, let's say changing zeros and 1. We have the same measurement operator, so projection on state 0, but now acting on the 1 from this state times unity operator on the 1 from qubit B. This is equal to 0. This is equal to 1. So what we get in the end is the 1 divided by the square root of 2. The square of this gives us the probability 1/2 of gaining this measurement outcome. We have the state 0 that we measured on the qubit, and nothing happened here. So this is 0, the second term zeroed out. So we do have a correlation. If we measure that qubit A is in state 0, we automatically know that qubit B also has to be in state 0. If we do the same thing just with the other measurement outcome, then we will get something very analogous, but if qubit A was in state 1, then qubit B also was in state 1. An important bit here is that the measurement outcome on qubit A fully determines the state of qubit B, meaning that if we only look afterwards, if we measure the state of qubit B, we don't on the fully mixed density matrix. So actually, exactly the same thing happens. So it's density matrix, we need to use the operators, the measurement operators on both sides, but we know how it works. So what we get is we get the 1/2, and then we have 0, 0 on state of A, so on 0, 0, and the part from this bit 0, 0, times nothing happened from both sides on the state of qubit B. This gives us 1, this gives us 1, and then we have the second term, which is 0, 0, acting on 1, 1, acting on 0, 0, times nothing happens on qubit B. This is equal to 0, so we are left with probability 1/2, state 0 on qubit A, times state 0 on qubit B. If we do the other measurement, H1 row M1, then in the end we will get something analogous, just the outcome of state 1 on qubit A, predetermined outcome 1 on the qubit B. So you should say at this moment, what is supposed to be the difference? The difference is that if you change the basis of your measurement and no longer measure in this computational basis, then you will get an analogous result on the quantum state, but on the classically correlated state you will get no information. So if, let's say, your measurement basis of qubit A would be this one, so an equal superposition between 0 and 1 with either a plus or a minus sign, so this is a basis which is as different from our original 0 and 1 basis as it is possible, what we are going to get is, in the case of m plus, obviously m plus minus are again measurement on qubit A doing nothing on qubit B, and we act on this maximally entangled state. What we are going to get is a very analogous situation. So if we measure plus on qubit A, we automatically get a plus on qubit B, and same in case of the measurement of minus on 1, minus on 2. These states are orthogonal to each other. We got full information and full correlation. But if we do this on the mixed state, what we will get is probability 1/2, measurement outcome on qubit B, but an equal mixture on qubit, so measurement outcome on qubit A and an equal mixture on qubit B. So the 1 and a 2 qubit, a 1 in a single qubit basis is just 0, 0 plus 1, 1. If we do the other measurement, then we get 1/2 measurement outcome on qubit A, but the same state we got before on qubit B. So this is in fact the difference. This is the most striking result, because now in case of the classically correlated state, if we change the measurement basis, we get no information about the measurement outcome on qubit A in the state of qubit B, and in fact the measurement does change the state of qubit B, but what we get is a state which is, well, indeterminate, in the sense that it's just 0 with probability 1/2 and 1 with probability 1/2. So it turns out that if you are in this maximally mixed state, regardless of what measurement basis you choose, you are going to get full correlation between one and the other. So if your basis would be, I don't know, x, y, with x equal to alpha 0 plus beta 1, and y being the orthogonal state, so beta star 0 minus alpha star 1 is orthogonal to that. If you act with measurement mx on the maximally entangled state, then what you will get is x times some state which is going to be the complex conjugate, I lost my complex conjugate, yes, of x, and this x complex conjugate is alpha star 0 plus beta star 1, and if you do the other measurement, you will still get full information about state B in state 1 and the other way around. This one is defined the same. Okay, let's move on because we are running out of time. And let's try to quickly talk about teleportation. So, teleportation. So the idea here is that we have one qubit in an unknown system state alpha 0 plus beta 1, but we want the same state on qubit C without learning what this state actually is. So the idea behind the fact that this is teleportation is that particles are in principle indistinguishable, so what determines whether we are dealing with, well, the particle we want to be dealing with it is its state. So in this sense, we are trying to move the state, an electron, for instance, so some qubit with the state psi into location C, and apart from the location, it will be indistinguishable. Okay, and this is done via the help of a third qubit. See, we were missing B. And this third qubit, let's draw it closer to this qubit, and we want both of these, qubit B and qubit C, to be initially entangled, and this entanglement is going to help us teleport this unknown quantum state. We got used to C+, so let's use C+. So our initial state is C on qubit A, and it's maximally entangled state right there on qubit C. I'm still going to lose all of the labels and I'm going to use the location of 0 and 1 to identify the state. Okay, so this is alpha 0 plus beta 1 on qubit A, qubit B, now we can multiply all this, and this is 1 divided by square root of 2. Alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. And I'm still not doing anything. I mean, I'm just rewriting all this stuff, but the experimentalist is still standing there being bored and wondering what I'm doing. And what I'm doing is I'm going to rewrite this in such a way that I have the state of qubits A and B separately. So it's alpha 0, 0 times 0 on C, alpha 0, 1 times 1 on C, and so on, beta 1, 0 times 0 plus beta 1, 1 times 1. And because the Bell basis is just a different 2-qubit basis, we can take these states of qubits A and B and rewrite them in this Bell basis which we introduced earlier, and then we can order it in terms of um, of the Bell state. Them. So I have my Bell state separately. So I get Bell states plus times alpha 0 plus beta 1. The extra 1 divided by square root of 2 comes from here, plus psi minus alpha 0 minus beta 1 plus phi, okay, I always mix Greek letters, alpha 1 plus beta 0, and the fourth Bell state times the last combination, so alpha 1 minus, alpha 1 minus beta 0. And this is more or less the end of all the tricks in teleportation. Sorry about that. This is the moment that the experimentalist comes and measures together qubits A and qubit B in the Bell basis. So when the experimentalist measures this Bell states on A and B, then automatically, after reading out the outcome of the measurement, we know that we have the proper state that we wanted and that we don't know on qubit C. If we get this measure outcome, then we need to make a single qubit phase gate that will get rid of the minus. If we get this measurement outcome, we need to make the swap gate, which is going to swap qubit state 0 for qubit state 1. And if we get this measurement outcome, we need to correct for the qubit states being mixed and for the phase, but nevertheless, we can still do this by a single qubit operation of qubit C. And that's it. This is the whole of teleportation. It boils down experimentally or on a piece of paper where you don't feel like ordering all of this. It boils down to starting with the proper initial state, measuring qubits A and B in the Bell basis, and then, depending on the measurement outcome, just doing the proper quantum gate on is on the last qubit, and you have teleportation. So it's nice and simple. And actually, what did I do? Okay, one more comment here is that the reason we're talking about teleportation, apart from the fact that it was cited in the Nobel Prize, is that most of the quantum algorithms that are supposed to make computation faster actually operate on the same kind of principle as teleportation does. The entanglement allows us to do some operations simultaneously in the algorithm and then to distinguish between those things by performing the appropriate measurement that's going to guarantee what we want. Okay, so let's try to do Bell's inequality really fast. Okay, Bell's inequality. And actually, there is a full class of Bell's inequalities. It's not one Bell's inequality. We're going to be look at the one which was not proposed by Bell. This was the first one, but the one which is called the CHSH inequality. This comes from the last names of the authors: Clauser, Horn, Shimony, and Holt. And the reason we are looking at this inequality is because it's most straightforward and is closest to the measurement. So first we have to derive the Bell's inequality, and this is an inequality which holds for two particles that can have classical correlations, but in general it's an inequality that takes into some assumptions like locality and realism. But it's one of those things that you derive while making a lot of assumptions, but that everything sounds logical. So we start with two particles in some unknown state, and one of these particles is going to be sent to Alice, while the other particle is going to be sent to Bob. So it's one gets to be Q with A and the other one gets to be Q with B, and here they are making this distinction that they're far away, so they're definitely distinguishable. So we have qubit A, and this qubit A can be measured either in setting Q or in setting R. Whoops, that's not where I want to write. They're not. Okay. And so you can imagine this is an optical experiment and others measure the polarization of the photon, and he can set it to distinguish between vertical and horizontal polarization, as you can see in this way, and a lot of those we're going to assume, for simplicity's sake, and because the authors assume that this property Q, which we are measuring, can only take values plus and minus, so for, say, vertical and horizontal polarization, and also this other property can have values plus and minus, and one of the two measurements is performed after she gets her qubit, and this is chosen randomly. So on system B, Bob does the same thing, but he has his own set of I don't know why P is bad. He has his own systems, a set of two measurements between he chooses randomly, and these can also give him the outcome plus or minus 1. So now we are going to have a slightly weird quantity of interest, and this is going to, I'm going to label it B. They didn't do this, but if you don't do this, you have to rewrite all of these things a lot. So the the quantity of interest is the value of Q times the value of S plus the value of R times S plus R times T minus Q times T. So it's actually convenient to rewrite this for a moment as Q plus R times S plus Q minus R times T. And we can see that this value B can only be equal to plus or minus 2. Yes, I couldn't see it, so the easiest way to do this is to make a table. We have Q, R, okay, and then we have Q plus R, so what we have here, Q minus R, and then we're going to see us, taking into account that S and T can only be equal to plus or minus 1, we are going to look at B. So, let's see, if Q is 1 and R is 1, then this is equal to 1, this is equal to 0. 2 and 0. So depending on the value of S, B can be equal to plus or minus 2. Then we have 1 and minus 1. This is equal to 0, this is equal to 2. B again can be plus minus 2. You get where this is going. Minus 1, 1, 0, minus 2. And B can be equal to plus or minus 2. And the last one is similar. This is minus 2, 0, and again. Okay. Obviously has to be true. And now we are going to introduce the mean value of these quantities and P, which is going to be the probability that certain values of Q, R, S, and T, that Bob and Alice get certain values of Q, R, S, and T as their measurement outcomes, and obviously each of them can be plus and minus 1. So the average value of our quantity of interest is equal to the sum over all measurement outcomes with all probabilities, so all possible values of B depending on those parameters times the probability with the same stuff. So on one hand, I'm going to use this equation twice. This has to be lesser than equal to the sum of the probabilities times 2, because B can be either plus or minus 2, so plus 2 is the bigger one, so it has to be lesser than equal than 2. And on the other hand, so this is the inequality part of our Bell's inequality, and on the other hand, we can rewrite these probabilities as the sum I mixed something. We can rewrite this as the probability times Q times S plus PRS plus PRT minus PQT. So we can rewrite this as the mean value of QS plus mean value of RS plus mean value of RT minus mean value of QT. And here we got, by rewriting this, we get the Bell's inequality, which seems logical and should hold. So this is the CHSH Bell's inequality. Yeah, so the point of looking at this inequality is that, and the reason why it looks like, why people are looking at this one, is that if we choose the things that we measure in an appropriate way, and we take a maximally entangled 2-qubit state, we can break this inequality. We can violate it by pretty much. So we're going to be looking at this 2-qubit state, which is maximally entangled, and it's different Bell state that we used previously. And we're going to have 4 different measurements. So Q is going to be represented by the Q following matrix. The measure state 0 is +1, measure state 1 is -1, R sigma S. With this matrix, but if you diagonalize it, you will find that +1 outcome in the single qubit plus state and the -1 outcome in the minus state. Bob is not going to look so straightforward. The S measurement is minus sigma Z minus sigma X. They are slightly weird, but they are chosen, so it's going to work. So if you write this in matrix form, it's 1 divided by square root of 2 minus 1 minus 1 minus 1 plus 1. And if you diagonalize this, you will also find that in its eigenbasis, it takes this form. So you also have 2 measurement outcomes, one of it with value +1 and the other one with value -1. And the last one is sigma Z minus sigma X divided by square root of 2. And this looks very analogous. You just have the 1 in a different place. Obviously, you can also diagonalize it and also have this form, which means that we are in fact in a situation where the measurement outcomes are plus and minus 1. Okay, so we need to calculate the mean value. We are in quantum mechanics, so this is going to be reasonably straightforward. So if you want to calculate the mean value of QS, you need to take your Bell state and put it on both sides, obviously. And yeah, okay, fine, we can do 1 properly. So I have 1 divided by square root of 2 from both sides, from the psi. That's psi minus, okay. So I have 0, 1, minus 1, 0 times QS 0, 1, minus 1, 0. And again, we know we have to multiply all of this, and then we know that Q acts in the subspace of qubit A, S acts in the subspace of qubit B, so we can rewrite this as 1/2 0 Q 0 1 S 1 minus 0 Q 0 Q 1, 1s 0 minus 1q 0, 0s 1 plus 1q 1 0s 0, and then that's why I wrote these things in matrix form. Looking at this, well, this is obviously 1 0 0 minus 1. Here you automatically, just by reading of the proper matrix element, get what you wanted. So what you're going to get is 1/2. This is equal to 1. I feel I lost something. Okay. The other one is this S, and I want S element 1, 1. So I want this one times this. So it's 1 divided by square root of 2 plus 1. Of diagonal elements of this are equal to 0, so it's minus 0 minus 0, and here we have plus, this is minus 1, or square root, and again minus 1. So what we get is 1/2 times, yeah, so we get 1 divided by square root of 2. And you do it the same way for all of the other ones, and you get this one equal to 1 divided by square root of 2. This one, oops, t, is equal to 1 divided by square root of 2, but the last one, that's why everything was chosen this way, is equal to minus 1 divided by square root of 2. So the mean value over quantity of interest is this plus this plus this minus this, which means it's 4 divided by square root of 2, which is 2 times square root of 2, which is obviously greater than 2, so we just broke the Bell's inequality, which seemed so logical just a moment before. And yes, so if we had a separable state, all of the logic that we used a moment ago would work quite nice, but I think it's more interesting to compare this to our classically correlated state that we used before. So to this one, plus 1, 1, 1, 1. So if we do everything the same way as before, we will have Q, S, but now this means that we have a trace of rho times Q, S, then everything else is easy, and what we get in the end is 1/2 0, 0, Q, S, 0, 0, plus 1, 1, Q, S, 1, 1. What we don't have is the pesky tool case. everything is fine. I calculated this in piece earlier, and in the last one, which was kind of surprising, I don't do Bell's inequality normally. This one is still -1 divided by square root of 2. So if we calculate the mean value of our quantity of interest, it's 2 divided by the square root of 2, but it's not because of this. It's because of the diagonal ones. So it's equal to the square root of 2, which is smaller than 2, and everything is fine. So if you study this in more detail, it's possible to show that to break Bell's inequalities, you need quantum correlations. I just shown you an example that we had states. I actually should have chosen the other one, the 0, 0, 1, 0, 1, maximally correlated classical state, but I will get the same result, just that the two middle ones would be non-zero and the two these two would be 0. Should have thought about it earlier, but anyway, it's possible to show that quantum correlations are necessary to break Bell's inequality, whereas classical correlations are not going to do it. Okay, so the conclusion is that as long as you're dealing with 2 qubits and as long as you're dealing with 2 qubits and pure state, these things are dealing with entanglement is pretty straightforward, but this is enough to show that you can get pretty strange effects with the use of entanglement, and quantum correlations can allow you to do many more things than classical correlations allow you to do, like teleportation and like statistically strange phenomena like the breaking of different types of Bell inequalities. And as we are slowly seeing, these phenomena can actually be used for pretty useful things. So, thank you and goodbye.